Okay, November 2015, Standard Level Paper 2, about probability. It's quite an abstract one. These are quite common, these sorts of questions, where they just give you all the information about the probabilities algebraically, and it's really focusing on, can you interpret the notation and combine that with some rudimentary probability facts. So the first thing, part A, is asking you to do is evaluate the probability of C intersect D. Given the fact, this is a useful fact here, that C and D are independent, and we've got a value for the probability of C happening and a value for the probability of D happening. Because C and D are independent, and this is in the formula booklet for independent events, the probability of C and D happening is equal to the probability of C multiplied by the probability of D. So it's just a case of doing 2k multiplied by 3k squared, which is 6k cubed. Part B is just evaluating the value of k, because now we're told that PC intersect D, which we just worked out is 6k cubed, has the numerical value of 0.162. So 6k cubed is equal to 0.162. It's just a case of solving that. Divide both sides by 6. K cubed is equal to 0.27. Take the cube root of both sides, and you get k is equal to 0.3. That's part B. Part C is certainly the trickier part. Find the probability of not C given that D. The probability of not C given D. Now again, from your formula booklet, you can use this formula. The probability of A and B is equal to the probability of A given B multiplied by the probability of B. And most of those things we either know or can work out. Although, if you go to the end of this video, you'll see there's a faster, much faster way that relies on your understanding of probability to get this same result. So, I'm going to replace A in this expression with not C. So anywhere A appears, I'm going to write C, and anywhere B appears, I'm going to write D. So I get the probability of not C and D is equal to the probability of not C given D, which is the thing I'm trying to find, times the probability of D. Now, if we go all the way back to the top, we know the probability of D. It's 3k squared. Or, if we evaluate it, because we know the value of k is 0.3, then that is 0.27. So I can put that in as my value for probability of D, 0.27. The probability of C, not C, given let's move everything down a little bit so I'm not writing over the barcode. So we've got 0.27 there. We've got the probability of not C given D, which is the thing I'm trying to find. And then the last bit is, what's the probability of not C intersect D, of them both not happening? Well, they're independent, which means that I can calculate that just by doing what's the probability of C not happening multiplied by the probability of D happening. Well, the probability of C not happening is just 1 minus whatever C was, and we've got that at the top. Scroll all the way back up. It's 2k, so that's 0.6. Come on, move. 0.6, so that's 1 minus 0.6 times, we already looked at what D was, 0.27, I'm going to need brackets on that, is equal to the thing we're trying to find, C given D, times 0.27. Well, this bit in the brackets here, that's 0.4 times 0.27, and you may have already noticed that since I've got a 0.27 on both sides, I can divide by it. I can just cancel it basically. 0.27 cancels on both sides. My answer is that the probability of not C given D is equal to 0.4. But you could have gotten there much faster, because the probability of not C given D, since those two events are independent, that means D doesn't affect whether C happens or not. It also means D doesn't affect whether not C happens or not. So whether D happens or D doesn't happen, it doesn't change the probability of C happening or not happening. So because they're independent, this is a property of independence, the probability of not C given D is just the same as the probability of C, which we already said you can work out by doing 1 minus 0.6, which gives us the answer 0.4, and that's a shortcut instead of having to go through this sort of algebraic approach.